Let's say that we have an 8 GB memory with one word in memory getting stored in one cell that has a 32-bit address. We also have a 512 kilobyte cache with 64 bytes per line. We are trying to store in cache the word with memory address 0000E602 in base 16. The first thing we are going to do is convert this memory address to base 10. So we have two ones, 6 16 squares, and E, which means 14 times 16 cubes. So we add them all up and we get 58882. So we are trying to store the word in 58882 in cache.
So what we want to do is determine where in cache this word gets stored. So we're going to take the address in base 16 and write it in base 2. Each base 16 digit corresponds to 4 bits, and all of these zeros are 4 bits each. E is 14, so that's 1110. 6 is 0110. We have another 0. And 2 is 0010. Now we're going to divide this 32-bit address up into a tag, a line number, and a word number. This means we have to figure out how many bits are in the tag, how many bits are in the line number, and how many bits are in the word number. One useful number that we'll want to know is how many bytes are in each word. We know that the memory is 8 gigabytes, which is 2 to the power of 33 bytes in the main memory. We also know that the memory address is 32 bits, which means that there are 2 to the power of 32 words in total. 2 to the power of 33 divided by 2 to the power of 32 is 2, so there are 2 bytes in a word.
This lets us figure out how many bits are in the word number in the memory address.
Each line in the cache is 64 bytes, and there are 2 bytes in a word. So there must be 32 words per line in the cache. 32 is 2 to the power of 5, so there are 5 bits in each word number. Next, let's figure out the line number. The cache is 512 kilobytes, which is 2 to the 19 bytes. Each line is 64 bytes, which is 2 to the power of 6. 2 to the 19 divided by 2 to the 6 is 2 to the 13. So there are 2 to the 13 lines in the cache. This means that the line number has 13 bits.
So now we just have to figure out how many bits are in the tag. We know that the memory is always larger than the cache, and that the memory is 8 gig, so that's 2 to the power 33 bytes. And we know the cache is 2 to the power 19 bytes. So how many memory can fit in the cache? So we have 2 to the power 33 divided by 2 to the power 19, which gives us 2 to the power 14. So log base 2 of 2 to the power 14, we get 14.
So let's split our memory address up. The tag is the first 14 bits, then the line number is the next 13 bits, and the word number is the last 5 bits. Our tag is clearly 0. As you can see, the line number when you convert from binary to decimal is 1840. This is also the block number of the word stored in memory. Since the tag is 0, the word number when you convert from binary to decimal is 2.
One other thing we want to figure out is which other memory words are stored in cache when this particular word gets stored. When word 58882 gets stored in cache, its neighbors come with it. Specifically, everything in memory block 1840 gets stored in cache at once. Our word is word 2 within block 1840, as we already figured out. This means that word 0 in block 1840 has address 58882 minus 2, which is 58880. Since there are 32 lines per block, the last word in the block is word 31, which has the address 58880 plus 31, which equals 58911. This means that the words with memory addresses of 58880 through 58911 all get stored in cache at the same time.